Hello and welcome to a Minerick University video. Today we're going to interview a vendor, Mike Bryan of Nanomotion. For people who are new to the technology or new to the company, to understand what Nanomotion is, how it works, and what it's best used for. Mike, are you okay with an informal Q&A session on Nanomotion?
Sure, let's do it.
Alright. Let's start with, how does the Nanomotion motor work?
Sure. So what we do is we take a piezo crystal, which is what all of our motors are based off of. And we take that crystal, we hit it with some voltage, and we create what's technically called an ultrasonic standing wave. So we basically stimulate its resonance and get it to wiggle. And then we take a ceramic fingertip, preload it against the bearing structure, and get linear or rotary motion from it.
So in your presentations at the branches that you've made, we see that it's a frictional situation with what is an elliptical motion with this ceramic finger? And so a ceramic finger against a ceramic strip, and it just pushes it along.
Correct.
So it's a linear motion. You can hook it to a rotary stage, a circular apparatus, but it's still a thrust movement, right?
Correct.
Okay. So each of those fingers and the crystal's assembly is called a motor element, is that right?
Right.
What is the resolution of this system?
Sure. So the motor itself is just a forcer mechanism, so there's no resolution with the motor at all. But when you apply it with an encoder and a motion controller, we're capable of achieving moves down at the nanometer level.
So now nanometers, some people are confused by that. What is a nanometer?
Well, 1 nanometer is 1/1000th of a micron, which is 1/1000th of a millimeter.
Okay, so it's 10 to the minus 9th meters, right?
Correct.
All right, very good. What are the slowest and fastest speeds you can achieve with this technology?
The fastest speed is 300 millimeters per second, and that's the fastest today. And then the slow end, we've actually done below a micron per second, so hundreds of nanometers per second.
Interesting. 300. What'd you say? 300 millimeters per second on the fast?
Correct.
That's pretty good. How much force how much linear thrust can one of those fingers develop?
Each finger generates 1 pound of linear thrust force.
1 pound. So there's no torque. Always talking about thrust.
Correct.
Okay. How many motor elements, excuse me, if you have one motor element, do you need one drive per motor element?
You need one drive per axis, and we have a maximum of 32 elements that we can put on one axis.
Okay, so it can be one drive up to 32 motors.
Correct.
Okay, or 2 motor elements. With traditional servos, we have control modes. We have velocity, torque, and position. Tell me about how this compares.
This is going to compare to a velocity drive. So typically you're going to give us a plus or minus 10 volt command from a motion controller to control the velocity of the motor. The encoder loop gets fed back to the motion controller, which is where all the algorithms take place.
Okay, so the interface to the drives is the standard plus minus 10 volt analog signal?
Correct.
Okay. That was one of my questions. With this frictional system, you've got a ceramic finger rubbing a ceramic strip. Do either wear out?
They'll definitely generate some particulate. Keep in mind that particle count is very low and very small in size. For most people, it's not even a concern for them to even bring up. But it does go to the life expectancy of the system. Typically, we'll rate our motors for 20,000 hours of operating time. That's assuming a high velocity performance and high duty cycle. If you scale the velocity back, scale the duty cycle back, you can get much more life out of it.
20,000 hours, okay.
And that's in motion time. That's not sitting there enabled with no movement. That's only counts the time it's moving.
Okay. Now, during the time, when it makes its elliptical motion, it's pushing part of the time and moving back part of the time to push again. How does that affect the smoothness of the velocity or the thrust?
Sure. So you got to keep in mind that the frequency that this is happening at is 40 kilohertz. So nothing mechanical can even react to it. So with the inertia of the slide moving and the motor resonating at 40 kilohertz, you get a nice, smooth, constant velocity out of it.
Okay. Let's see. That frequency you talked about is 40 kilohertz. Does it introduce any mechanical vibration at all?
Not really. Once again, it's at such a high rate that the mechanics can't respond to it, therefore they don't see it. It's quite possible you may see some subharmonics of that frequency, but we have yet to find an application where it's been a problem.
Okay. And how do you size Nanomotion? Is there software? Are there speed thrust curves?
There are speed force curves in our catalog and in the motor manuals. We use an simple Excel spreadsheet to do our sizing. We size it to F equals MA, so we break it down in the most basic form of sizing.
Okay, very good. So now, to kind of wrap up, this is a mechanical system, frictionally based, so there's no dither, right?
Correct. So inside every motor there's a series of springs that help lock that piezo crystal onto the moving mass substrate, if you will. So we have a very high static stiffness. There's no dither. You know, a traditional encoder is going to bounce between encoder pulses to maintain position. We don't do that.
Okay.
We use those springs to do that for us.
And when it's holding something in place, there's no current being drawn, right? It's a mechanical.
Correct. No current, no heat.
All right, very good. Well, that brings me to my last series, my last question, really. What are the types of applications that Nanomotion's used in?
You know, really, if you break it down, there's 6 kind of categories of benefits of why we participate in the market. The first 2 is our ability to make high-resolution moves, to do nanometer level work, and the other one is to be able to work in special environments like vacuum and non-magnetic. Those 2 are probably the most common, you know, reasons why people think of Nanomotion.
Yeah, the Nanomotion name would lend you to think that, or lead you to think that high resolution is what you do, right?
It is something that we do very well, but it's not what we do most often. What we do most often is provide people with a mechanical assembly that gives them a high static stiffness. Once again, we're using those springs in the motor to give them a nice stable platform to do their work on.
To hold position.
Correct.
All right.
The other one would be constant velocity. We give them the ability to make a very smooth constant velocity scan, whether they're doing imaging or things like that. We also give them the ability to move and settle quickly. You know, this is, for all practical purposes, a solid-state motor, so we can get out of the hole much quicker, because once that crystal gets that 40 kilohertz sine wave, it's moving. It has no choice. And then on the deceleration side, because we're friction-based, we use that to our advantage to help brake and decelerate that load quicker. So we can make point-to-point moves quicker than other motor technology can. And then really probably the most common thing that people use us for is our size. You know, we give them the ability to generate a lot of force in a very small package.
So even if it's not a nanotechnology or a nanomotion application, just because it's a small motor and produces a pound of thrust, you can use it, right?
Right. We give the machine builder the ability to make the same machine smaller, therefore occupying less real estate in a laboratory or factory environment.
All right, very good. Well, I hope that's helped anyone watching understand what the Nanomotion technology is, how it works, and what it's good for. Thanks, Mike, for being here.
No problem. Thank you.